Graphisoft offers outstanding tools that support a smooth all-around workflow for architects. But architects don't live in a hermetic world. They have to cooperate with partners in other segments of the wider AEC workflow. This presentation focuses on what Graphisoft offers their users in the way of multidisciplinary interoperability. Or in other words, let's talk a little bit about how the Open BIM concept works in practice. 3 years ago, McGraw-Hill ran a survey about BIM, and the top wish from the vendors was for improved BIM solutions for interoperability with other software applications. Now, let's see why this came up as the #1 issue. There are simple reasons for this. Architects have different requirements for their BIM than engineers, and that's why the modeling conventions and the internal logic of the model may differ significantly. So, it's important to note that the architectural BIM is not the same as the BIM of other disciplines. Typically, engineering applications, for example the structural, the mechanical, and energy design applications, are different in each country. Engineers naturally prefer programs that support the standards of their own country, and these are usually specific local applications. How can we ensure that an architectural program like ArchiCAD is able to work together with hundreds of local engineering programs? Which conditions must be met to achieve interoperability? There are 2 key conditions for interoperability to work. 1. Support for the so-called reference model, and 2. Support for an open source yet standardized data exchange format that has quality requirements. The so-called Open BIM concept provides an answer. This is nothing other than the implementation of the reference model on an open platform. First, let's take a look at what reference model means, on which interoperability among professions is based. Each discipline is responsible for its own work. For example, the structural engineer is responsible for the load-bearing parts of the building. He or she calculates for the local design standards. This consideration requires that each discipline be able to edit and modify only its own model, while using the others' models only as a protected reference alongside their own. As we've mentioned, the models coming from various disciplines, even if they may seem similar at first glance, are in fact quite distinct in their details. This is especially typical of the exchange between the architect and the structural engineer. Here's a common example. The architects define the contour of a slab, for example a slab element, while the structural engineer, doing design calculations with available building elements, such as hollow core concrete slab panels, defines the local bearing structure. In this picture, we see that in the structural model, several slab elements, which might even be modeled using beams, replace the single slab element used by the architect. In other words, even in this simple slab example, we can see several differences between the 2 model types, in the element type used, in their size, and in the number of elements used. We could cite many other examples of differences between the models used by the disciplines. For example, the pictures show differences, not just in the level of detail in the intersections, stiffeners, element connections, supports, but also in the relative positions of the elements. After all, it's the structural engineer who determines the final position of the load-bearing elements as calculated using the given loads and environmental conditions. To summarize, the different responsibilities and model types among the various disciplines demand the use of and adherence to the reference model concept. For example, the following basic tenet must be observed. Data loss in geometry and data is not allowed. The geometry part means that an element of the reference model must be shown in our project with its original geometry and at its original position. The data part does not mean that the reference model has to contain all the data that's important to the other disciplines, only the data relevant to one's own project. For example, relevant data for an architect includes the exact material and profile data defined by the structural engineer in the structural model. Now let's take a look at the various open code file format possibilities and which requirements must be met. ArchiCAD is able to read and write many data exchange formats. Among these, how do we choose the right format for interdisciplinary collaboration? Which requirements and considerations must the format fulfill? It must support the element's 3D representation. It must be able to store data. And it's not enough that it includes a large database. The database must be filterable so that each discipline can extract just the data that it considers important. It must fulfill the requirements of the reference model concept. The format code must be open to any software developer. This is necessary to ensure global collaboration among local programs as well as the major ones. To enable fast code implementation, the code must have a simple scheme structure. In order that the code be understandable and implemented anywhere in the world, its language must be English. This does not mean, however, that it should not be possible to localize, for example, the standard properties for various countries. Among the various available file formats, it is Industry Foundation Classes, or IFC, which meets all of these requirements. IFC has been developed by Building Smart, a nonprofit industry-led organization, since 1994. Each building or HVAC object type has 3D geometry representation in the IFC standard. The IFC scheme contains hundreds of predefined standard properties by object type, but you may define any number of custom properties without limitation. Although the IFC database can be very large, it is easily filterable with a simple user interface. All vendors accept IFC as a standard that fulfills the reference model concept. IFC is an open, neutral, and standardized specification for building information modeling, or BIM. As an open format, IFC does not belong to a single software vendor. It's neutral and independent of a particular vendor's plans for software development. The IFC format is registered by ISO. The IFC scheme structure is very simple. It's so simple that you can even check the content of an IFC model using a text editor. The IFC code language is in English, but some countries have already begun translating the property names into their local language. IFC defines multiple file formats that may be used, supporting various encodings of the same underlying data. Besides the most widely used .ifc format, it has an XML format which is suitable for interoperability with XML tools, for example cost estimation and facility management applications, and exchanging partial building models. Both IFC formats can be compressed in a zip format in cases of huge project models and databases. An IFC scheme is basically a large code. Imagine a big, thick book in which each chapter describes a particular data exchange workflow. For example, one chapter includes the specification for sharing of building information models among the disciplines of architecture, structural engineering, and building services. Another chapter defines the data requirements for facility management, for example, how to describe the space containment and the base quantities of its members. Another chapter sets the rules for sharing models for energy analysis purposes, for example, how to export the relation between the spaces and the building elements that surround them. Each of these chapters is called Model View Definition, so a Model View Definition defines a legal subset of the IFC scheme and provides implementation guidance or agreements for all IFC concepts, classes, attributes, relationships, property sets, quantity definitions, etc., used within this subset. The official names of these Model View definitions are Coordination View, Basic FM Handover View, and Space Boundary Add-on View. These Model View definitions are the most important ones for architects and hence for an architectural application. In the U.S., for example, the space boundary-based IFC data exchange is required for federal contracts. The basic FM handover-based IFC database is the starting point for the COBE documentation standard required in many English-speaking countries. COBE stands for Construction Operations Building Information Exchange. And currently, the most widely implemented IFC view is the Coordination View, the foremost tool for sharing building information using the reference model concept among the different disciplines all over the world. ArchiCAD supports all of these major model view definitions. Just some notes. The summary line of this application table shows that about 150 applications have already been registered as IFC file supporters at Building Smart. ArchiCAD also uses and offers the Coordination View IFC Exchange format for collaborating with Revit's structural and MEP applications. To fine-tune the bidirectional IFC database exchange between ArchiCAD and Revit Structure MEP applications, Graphisoft has developed an add-in that manages IFC import and export on the Revit interface. This add-in is available for free on the Graphisoft website. How can the users of design software be sure that their software is compliant with the proper IFC standard and truly interoperable? For this purpose, there are official certification processes for each model view definition, run either by Building Smart or by the organizations who defined the actual model view definition. In this certification process, the participant software products are tested for how well they fulfill the requirements of the model view definition. Graphisoft is committed to ensuring that its products are professionally certified. To this end, Graphisoft takes part in the key challenges which test IFC capabilities. Significantly, ArchiCAD is the first architectural software to be certified compliant with the import and export requirements of the latest Coordination View 2.0. Typically, though, software users also test how well they're able to share their models with other professionals. One such example is the detailed study undertaken by the Vienna University of Technology in Austria, which tested the interoperability capabilities of 12 design and analysis applications, specifically whether giving building element types retained their geometry during export and import operations. This graphic presents a summary of whether the applications are capable of reading surface elements with special geometries imported from ArchiCAD, and if so, the quality of the import. One British firm, Bond Bryan Architects, used 2 IFC model checker programs on a specific project to test the data exchange between ArchiCAD and Revit on an ongoing basis. They concluded that IFC can and does work on the vast majority of products, and we must all be able to use the software of our choice. In other words, we have to know and learn the interoperability skills of the BIM applications we use. Thanks to the IFC Open Platform, all disciplines are able to cover the data exchange workflows of the schematic design, the design development, and the construction documentation phases in the 3D model-based intelligent mode. Let's see, for example, the requirements and the details of the structural architectural data exchange workflow. This is much more complicated than the workflow between the mechanical engineer and the architect, because there's a great deal of overlap between the structural engineer and the architect regarding building planning. On the other hand, the MEP model, apart from collision detection, is quite distinct from the models of the other disciplines. Different structural applications have different functions, and these applications must be able to share data with architects. This data connection involves more than a simple two-way model exchange. It must be able to manage changes in the models, and this is a cyclical process with many iterations. The main functional requirements of the data exchange: create the model for each discipline, assign types to elements and classify their functions so that the other discipline will recognize my model elements in its own environment, filter elements and data. For export, I should only export the data that the other discipline needs. For example, accessories such as a fence, bench, or parked car, these are not part of the model's load-bearing structure. The structural engineer does not need a detailed window structure when the window's bounding box will suffice. For import, if I receive a large database, I should filter for the information that I need. Export the models. Import the model and place it as a reference model into each receiving application. Change management. That is, managing the version changes in each discipline's model. This graphic shows an example of element classification and export filtering in ArchiCAD. With a single click to access the Publisher tool, I can export just the load-bearing elements to the structural engineer who uses Tekla Structures, the building model with their spaces and functions to the mechanical engineer who uses Revit MEP, and the entire project, the building plus its surroundings, to the CAD manager who uses a model checker like Solibri. Here are the main steps of the architectural structural workflow in greater detail. 1. Architects create the first model according to the client's request in the given site. 2. To prepare the model export, architects filter the structural elements by using element and function classification, layer combinations, and display settings. Of course, the whole building without any filtering can be exported as well, and the structural engineer will do any additional model filtering. 3. Architects export the filtered model in IFC file format. 4. Engineers receive the architectural model and insert it as a reference. The complete model or just certain elements of selected architectural layers can be imported. 5. Engineers define the structural model and its details based on the referenced architectural model. They can also generate analytical models for analysis applications. Engineers query the initial profiles and materials defined by the architects. 6. The completed structural model or its filtered part is exported back to the architects. 7. Engineers also use IFC file format for the model exchange. 8. Architects merge the structural model into their current project. Filtering is available for the import, and imported elements can be placed onto specified layers. By default, the new imported elements will be protected in accordance to the reference model concept. Architects may compare the two model types as two view sets. One contains the architectural model, and the other contains the imported structural model. Architects query the profiles and materials decided on by the engineers. 9. Architects modify or update their project according to the imported reference model. 10. They export a new IFC file based on the project's new status. 11. The new architectural model is imported to the current structural environment as a new version of the reference model. It's compared with the old reference model version. The differences are displayed as new, deleted, and changed elements. 12. Engineers update their project, both the model and the calculations, based on the detected differences. 13. The engineers send the new structural model version back to the architects. 14. Architects compare the new structural model version with the previous one. 15. The comparison process automatically merges the detected changes only, so the new, modified, and deleted elements just act as a reference to the architect's running project. 16. Architects can easily check the changes recommended by the structural engineer and can make modifications to update the design manually or by using structural elements as real ArchiCAD elements. As we can see, this collaboration is not just the simple exchange of models in both directions. Instead, it involves complex operations such as the cyclically repeated comparison and update processes. Finally, the two disciplines make their own or combined documentations. Let's look at an example of the architectural structural exchange and another example of the architectural MEP exchange in two real open BIM projects. We'll consider a specific geographical region and the local programs that are commonly used there for building design. In Scandinavia, a leader in the IFC world, 3D-based model exchange is commonplace, using the popular applications listed here. The first example is from Norway. The architect, Rift AS Architects, designed the Nordre Jarlsberg Brygge complex by a fjord in Oslo. It's a high-end residential complex with over 1,000 units, including apartments, offices, a hotel, a kindergarten, restaurants, and shops, as well as other amenities. Rift Studio is a creative and dynamic architectural studio that knows that using the latest technology saves time and money. The firm implemented the BIM workflow with the help of ArchiCAD in 2008 as a way to create and document architectural design at a professional level. The project was designed with ArchiCAD and Tekla Structures, taking advantage of the features of 3D-based collaboration, 3D models, and IFC technology, provided full control for Rift Studio in the design and construction of complex projects. In addition, the 3D model helped with sales too. The sales team was able to pinpoint, for example with sun studies, which apartments would have nice views of the fjord and those that were perhaps less desirable. Let's take a look at the live BIM elements of the project in the two different professional design programs. Here you can see a 3D view of the entire architectural model in ArchiCAD, and here just the buildings without the site environment. Let's zoom in on part of this residential project. As mentioned, the first step of the Open BIM workflow is element filtering and classification. The architectural design must be shared in a way that meets the requirements of the receiving party, in this case, the structural engineers using Tekla Structures. In other words, the architects want to export only the load-bearing elements that are necessary for structural engineers. To perform a quick and fully automatic element filtering, it's important that all the elements in the architectural model have the appropriate element and load-bearing function classification. For instance, let's select this slab and check its settings. The function classification of this particular slab defines its load-bearing status according to the role in the design. These element-level classification settings have a direct effect on the content of the exported IFC file. The load-bearing properties of the elements represent a standard IFC property, which are interpreted accordingly by all IFC-certified applications. Another important aspect of element classification is element type. For instance, this slab was created by the Slab tool of ArchiCAD, so its default element type classification is set to slab, which is also a native IFC entity called IFC slab. But the element type classification could also be set to ceiling if we had used the Slab tool to model suspended ceilings in our project. Custom properties can also be created if required by the engineers or consultants who work with the exported file. For instance, acoustic and fire ratings can be set for every individual element as standard custom IFC properties. Using standard profile names, for example for columns and beams, greatly helps the work of the structural engineers. ArchiCAD has a built-in steel profile catalog containing thousands of standard steel profiles grouped by country codes and shapes, which can be easily assigned to the project beams and columns. Standard naming helps the structural applications to recognize the architectural profile, which is the first step in creating native structural elements out of the referenced architectural items. The partial structural display option helps the architects to display, using just one mouse click, only the elements having the classified load-bearing function. Here you see just the elements classified as load-bearing elements. In the case of a composite structural element, only its core, the load-bearing part, is displayed. The window and door elements can also be hidden, and only their nominal opening will be displayed, since typically structural engineers require this. Thanks to the WYSIWYG, or what you see is what you get, export concept of ArchiCAD, the elements visible on the screen can now be exported for the structural engineers in IFC file format. Just apply the simple Save As command for an IFC file format type. Let's select the IFC zip file format, which produces a compressed IFC file that's easy to send to the engineers by email. To ensure a one-click IFC export for those architects not interested in the IFC code and technology details, ArchiCAD offers predefined export settings. We call them IFC translators, by discipline and by specific application. Let's use the export preset that's optimized for IFC import by Tekla Structures. Of course, the architects can also decide if they wish to export the entire project or only some selected elements. Let's export the visible elements only now, just the load-bearing elements seen in the current 3D view, and send it to the structural engineers using Tekla Structures. Here, the architectural IFC project model is merged as a reference model to Tekla Structures. Let's have a closer look at the reference model elements. You can see the detailed properties of an architectural column element, for instance, the initial material, profile name that the architect set, etc. Structural engineers easily pick points of the elements, query info about elements shown to be for a column element, measure length and sizes, etc. The structural model can be created by Tekla's modeling tools by using the fact that the reference model, with its points and solid objects, lives in the structural environment. Reference elements can also be copied into the structural model as native elements. Tekla calls this function object conversion. This function converts, for example, the selected slab, wall, and column elements into real structural elements. A report summarizes the results of the conversion process. For example, it lists the recognized and convertible architectural profiles. Finally, the BIM tools of Tekla Structures build up the detailed structural model. Here you can clearly see the difference that we talked about between the architectural model and the structural model. For instance, how an architectural monolithic slab is modeled as a group of hollow core reinforced concrete planks. The rest of the architectural elements are also converted into their corresponding structural equivalents, as you can see on the screen. The structural engineer can now start the work by creating the analysis and design model and share it with structural analysis applications which do steel, concrete, or timber design according to local load and displacement stress limit requirements. Once the structural design reaches a certain stage, the structural engineer can transfer the model back to the architects. Architects can open the structural model as a standalone project, or they can merge the IFC model to the existing architectural project. Now we show the merge process. Start the merge command and apply it to the imported IFC file. Let's use a proper IFC translator that contains predefined settings for the import process. Selecting the translator optimized for the Tekla Structures connection places the IFC model on a layer system, which keeps the original layer names of the imported IFC file and adds the Tekla extension to them. Also, material conversion between the Tekla-named IFC materials and the ArchiCAD materials is done automatically. ArchiCAD provides a complete solution for the ownership of the models. The work of the structural engineer can be easily distinguished at any time and in any view of the project. So the structural model can be displayed either as a protected reference model or as an editable part of the project in views, 3D window, floor plan, section, and elevation views. Thanks to layer settings, now all the architectural elements will be displayed in wireframe, while the elements created by Tekla Structures are displayed by solid colors. Let's zoom in on some details of the referenced structural model. We can see the detailed concrete hollow core slab panels, steel columns with hollow sections, etc. All the fine details are successfully imported and correctly positioned by ArchiCAD. Architects can query the properties of the elements that arrived from the structural model. For example, selecting this balcony slab, they can check its properties set by the structural engineer, such as the material, sizes, and other IFC properties. If the structural model contains steel connections, including bolts or reinforcement bars and meshes, ArchiCAD can of course display them together with the building elements as part of the reference model. The merged structural model can also be displayed on the floor plan or in sections. Let's open a section view of the architectural model. With ArchiCAD's Trace and Reference tool, the architectural elements can be overlaid with the structural elements, for example in red. With the help of the slider, we can visually identify any inconsistencies between the two models. A real collaboration workflow is bidirectional and dynamic, meaning there are continuous round-trip iterations. To fulfill this requirement, open collaboration requires workflow-level support for change management, where existing, new, modified, and deleted elements are handled intelligently. For example, ArchiCAD and Tekla Structures can compare two versions of a structural or architectural model. ArchiCAD merges only the changes into the project for later checking. It collects the detected changes grouped by status and different colors. The geometric and position changes are displayed as modified elements in pairs. The new and deleted elements are also highlighted with different colors. In this example, the solar shading system of this balcony part is modified, reduced, so two columns were deleted, one new column was added, and the roof size was modified by the structural engineer. Architects can accept or reject the changes suggested by the structural engineer in the architectural and/or referenced model environment. The second example is also from Norway, based on a design created by a Swedish firm, Link Architecture. This project was carried out in the city of Kristiansand, involving a 5-story building complex of about 24,000 square meters, about 14,000 square meters of office space, and a 2-level underground parking area of about 10,000 square meters. The building, which has been completed, was designed completely in ArchiCAD, while the MEP design was done with Revit MEP. The different professions used IFC files to collaborate. This is the architectural model, where the air diffusers are being distributed for the ceiling plan. Although ArchiCAD's object library contains numerous MEP elements, the MEP Modeler add-on developed by Graphisoft allows for the modeling of MEP systems in 3D. The architects then sent their architectural model to the MEP engineers, together with the zone functions and air diffuser distribution. The MEP engineers were asked to design the air ventilation system, including dimensioning the duct system that ties the air diffusers together. For this data exchange, they used the export options, the built-in translator, optimized for Revit MEP. The MEP engineers open the architectural model in Revit with the geometry perfectly imported. The MEP design can then be carried out on the model as a separate discipline. The resulting duct system can then be exported with a single click, using the add-in developed by Graphisoft specifically for use with Revit. This add-in improves the MEP IFC model in several ways. For example, it coordinates the renovation status data between ArchiCAD and Revit, and improves the MEP system so that ArchiCAD can import the duct elements not as simple solid objects, but rather as intelligent equipment-type elements. Using the MEP modeler environment within ArchiCAD, the architect merges the MEP engineer's data into her own project. The merge process automatically matches layers and stories and places the new MEP system elements into the right position within the architectural model environment. It also warns the user that the imported elements won't be seen by default because their renovation status is set to new. The duct elements behave as intelligent parametric elements in ArchiCAD. The data and calculations exported by Revit can also be queried in ArchiCAD. The MEP modeler's collision detection function can identify any collisions with the MEP elements that have been referenced in. This allows the architect to easily adjust or change her model, for example, to accommodate the final MEP system. For example, here, a duct collides with a wall because the MEP engineer designed a larger duct than the hole planned by the architect. Of course, this is easy to fix, for example, by increasing the hole diameter. We can run collision detection once more to ensure that the fix was successful. We have seen the OpenBIM workflow in action, but OpenBIM is not just a technological tool for model exchange. It has grown into a movement. A few BIM software vendors, including Graphisoft as a founding vendor, have launched OpenBIM as a key part of their program. The program's goals and details are available from the Graphisoft website. The main goal of the global program is to help remote open collaboration workflows throughout the AEC industry. So, the OpenBIM program is a universal approach to the collaborative design, realization, and building operation based on open standards and workflows. The program provides common definitions and requirements for implementing OpenBIM collaboration. The program also defines the rules of promoting the OpenBIM message. The founding vendors defined an OpenBIM program guide. And who are the founding software vendors? Here they are. But it's not only the OpenBIM vendors who spread the OpenBIM message around the world at expos and conferences. Many partners have joined in. For example, Graphisoft's partner firm Advent conducted a roadshow in France to provide live demonstrations of OpenBIM workflow among various software programs. Here, Cubus, Graphisoft's partner in Holland, discusses open standard-based exchange among BIM design programs at a trade show. The other vendor partners have joined in. Here, the international firm Construsoft, which sells the Tekla Structures program, describes the advantages of OpenBIM collaboration. Almost every year, an international contest open to anyone is held under the name of OpenBIM Event. This is a 48-hour virtual design collaboration that promotes the power of collaborative working in the cloud and international developments in interoperability. It demonstrates the power of these new paradigms for architecture, engineering, planning, and construction. Through cloud-based collaboration, the event is open to worldwide participation. For example, here is a project proposal prepared for the Build Sydney Live event organized in October 2013. It was submitted by the team of ArchiCAD clients Rice Daubney of Australia and Obayashi of Japan, and it won the competition in the Best Use of BIM for Design, Drama, and Excitement category. This is a flowchart showing the steps of the project's development as carried out by the design team who were located in Sydney and Tokyo. There was a 48-hour open voice connection between the Australian and Japanese offices for continuous design collaboration, and all data management and data exchange was done in real time. They used 12 different types of software during the project. And blog chats dedicated to collaboration among these professions are growing in number. Open BIM, technology, movement. It's not just a fun accessory to the design progress. It's a clearly defined, results-oriented concrete direction that is also modern and trendy. Visit our website for more information about Open BIM, plus more videos on how different BIM applications share model and information among different disciplines. Use, enjoy, and join Open BIM. Thank you for your attention.